We'll first start with Thomas Kodger. He is still a young scientist, but a little bit more advanced. He is an assistant professor at the Department of Physical Chemistry and Soft Matters. He did his PhD in Harvard on applied physics. He also worked at a company, and now since 2017 he moved to Wageningen, doing some more fundamental research. So I think he's the right person to show the balance between fundamental and maybe applied research. Thomas, the floor is yours.
Good morning, everybody. Today I get the pleasure, before we hear from our PhD students, the pleasure to address with you not only the beauty of fundamental science, but also, I would say, the awesome responsibility that fundamental science has in society. So I'm, as introduced by Erko, I'm from the Physical Chemistry and Soft Matter group. But what actually is soft matter? Is it fundamental research? Is it applied research? Is there a really good distinction between the two? Erko offered a definition. I'm going to try and make it a little less obvious that there is a good definition. Sometimes we're searching for terminologies to define certain people in certain areas. My research group in physical chemistry and soft matter is one of the chair groups that works in soft matter. We also have chair groups in food physics, food process engineering, and bio-nanotechnology. And each one of us, the professors in these groups, exists kind of on a spectrum between applied and fundamental science. I became personally interested in soft matter research because I think it really connects fundamental science to life. So in soft matter, we work on materials that are common to everyday life, things like toothpaste, foods like mayonnaise, but also technological materials like car tires, and even items, things like that have no relevant value, but they have good aesthetic purposes, things that we take pleasure from, like art. And each one of these items has a parallel in fundamental science that we can ask really good questions about, really interesting questions. So in the case of toothpaste in the bottom left, we can ask questions about how are the particles connected to elicit this mechanical response that gives rise to the properties of toothpaste that we know. In the case of mayonnaise, how do we prevent the coalescence that occurs on these really fast timescales, or even study coalescence processes? In car tires, we can ask questions about what sets the inherent stiffness in these materials. Is this has to do with the local polymer topology, shown here in the bottom middle? Or even in the case of in portraits or paintings, we can ask how do we understand the complex dynamics of watching paint dry, which is actually more interesting than it sounds. Truly, you have to trust me on that. All of these fundamental topics essentially try and deliver something like what I call design principles. These are fundamental insights that allow us to do something in the future. So to give you two examples in soft matter, two historical examples, let's start with one that was developed in the mid-80s by two professors, Professor Pusey and Van Meeken, and they tried to ask a very fundamental question. If I take particles in solution and I increase their number density, at what point does crystallization occur? When do I go from a liquid to an ordered solid? This is such a fundamental question that this is actually the first computer simulation that was ever done back during the Manhattan Project. So what you can see in this image from left to right in these different vials is that the particle number density increases. And at a certain point, you start to see crystals. These crystals show up as these beautiful colored refractive objects. What you can also see in the image is that the crystals always go to the top. Now why is this? This is an unfortunate consequence of colloids, as the particles themselves are less dense than the solution that's around them, and they cream or rise to the top. About 10 years later, another professor, Paul Chaikin, really asked another fundamental question building on this. Well, how much does this creaming or rising to the top affect these phase boundaries that occur? In order to answer this question, he had to take these exact same samples and go to a really extreme location. He went to the International Space Station. So if you take the same, what he found was if you take the exact same vial number 10 in this case, put it on Earth on the left, you can see that there's no crystals forming. And on the right, in microgravity, about 6 orders of magnitude slower gravity in the International Space Station, you see these beautiful dendritic crystals here in this inset. Thus, you kind of refine the design principles of where these phase boundaries occur. Another beautiful example is in the area of liquid crystals. Now, many researchers have worked on this for many decades. One in particular, Kodger, who's sometimes often referred as the founding father of soft matter. He worked specifically in trying to understand defects in liquid crystals. How do these defects arise, and how do we eliminate them? That's all of these interesting called Maltese crosses that occur in this liquid crystal image. Now, hopefully I don't need to explain to you which one of these two fundamental studies had really a profound impact on society. I think it's quite obvious. Obviously, it's the area of liquid crystals. Not so much in the colloidal crystallization. But both of these required enormous amounts of effort. Effort not only in the way of financial effort of sending samples to the International Space Station, but also effort in thought. It took decades of understanding and research, fundamental research, to get to this point. So this comes to the kind of the key question, I would say, about fundamental research. Where does curiosity-driven research go? Does it need to have a purpose? Does it need to have a story? Does it need to have a goal? Can in current society, with our current topics of problems, can we actually support fundamental research? Some of those problems involve things like pollinator loss, climate change, over pesticide use, energy uses, sustainability, searching for real sustainable goals, habitat loss, and of course, the most imminent topic of today, the spread of coronavirus. With really a limited fundamental research budget, or fundamental research budget, do we ever have to make a choice between funding fundamental science and funding research to solve these problems? Hopefully the answer to that question is never yes. Hopefully there's always space for fundamental research. But as fundamental researchers, we really also need to be aware. We can't just avoid these topics. We can't stick our heads in the ground. Isn't it almost irresponsible of us to simply ignore these problems? Shouldn't we be out in front? Shouldn't we be leading the pack? Shouldn't we be deciding how to solve these problems ourselves? Too often, in my own experience, I've seen fundamental scientists look inward for problems that they want to ask for, when we should actually be looking outward to the world. As a consequence of these actions, there's this perception, I think, in society that fundamental research is somehow disconnected. This is a really big problem that we need to solve. Well, let's take it a step back for a bit, specifically take a step back in time. Hans Lieberman, who unfortunately is no longer with us, he wasn't the founding chair of my research group, but he certainly dominated the research topic for decades. He essentially literally wrote the book, or in this case many books, on fundamental and interface colloid science. He spent most of his entire career focused on one particular topic, on the electrical double layer. But his curiosity wasn't just unfounded. He constantly tried to make connections between this fundamental research and real topics, things like bacteria adhesion or nutrient and ion transport in soils. I think in general, if we don't follow Hans's example and we don't try and make connections between fundamental science and applied research, we're essentially lost as fundamental researchers. Said differently, we generate a lot of knowledge, but this knowledge can be in a very linear direction with no clear purpose. Same is also true in applied science. The ideal case is actually what we hopefully have here in Wageningen. That we have fundamental science that can illuminate some of these fundamental design principles that then feed back into applied science that then generate new fundamental research questions that we can solve. Essentially what we'll tell you today is that there needs to be a balance between both applied and fundamental research. If we don't have both, we simply won't get where we are going. This maybe sounds good to you. Hopefully many of you agree with this philosophy that I have. The question is how do we do this? How do we change this perception of a fundamental science from something that is considered obscure to something that is really working on today's problems? My solution to this problem is through the area of materials. Materials are really tangible objects, things that you can touch and feel, things that the public understands. But in order to really make new fundamental materials, we need to know where to make compromises. Compromises are always necessary. But in order to know where we need to do this, we need to really understand, again, these fundamental design principles. So now I'd like to give you an example from my own research in the area of color. So hopefully everyone appreciates color, me less so. I'm colorblind, actually, which is why this topic is very interesting. But color falls into two different categories, absorptive color and photonic color. We experience absorptive color almost every day. Also in beautiful paintings like this Van Gogh, where he used essentially minerals or elements, like things like cobalt blau, that happen to be very toxic, in order to elicit this beautiful absorptive color that he used. Nature, however, takes a different approach. In some cases, like this beautiful butterfly wing, this green butterfly wing, is not actually built in absorptive color, but what we call photonic color. So these photonic color are made up of basic building blocks, in this case keratin, that is ordered by nature in a specific way to give this periodic porous structure that actually reflects light, in this case reflects the green that we see from the butterfly wing. One of the interesting aspects of photonic color is because it's structural, it should last forever. So here's a beautiful example that I'll share with you. This is left here is an image of a fossilized bird wing that was found relatively close by in Darmstadt in Germany. This bird feather has been around for 30 million years. It's still bright blue in color. Inside this bird feather used to be these things called melanocytes, which created organelles called melanosomes. That's the image you see on the right. Inside these melanosomes is a large concentration of melanin, which scatters the light, which is what we need for photonic color. But they're also uniform in size, which gives rise to this beautiful blue color that we see. I struggled for a long time to find why mankind can't do this, why nature is the only use of photonic color. To give you only one example, I could only find one example. This is in the case of Lexus Blue. Lexus Blue is obviously developed by the Lexus car company. It took 15 years to develop. I don't know how much research money. It's extremely complicated to make. It's only found in the most expensive cars. Why is that? I would claim that this is because we don't understand the fundamental design principles behind the origin of this photonic color. And the only way to solve this is by doing a lot of empirical research, which is what Lexus did. So what my research group tried to set out and do is, okay, how do we establish the fundamental design principles to make photonic color in the lab? So to start off, we kind of have two approaches. One, you or me, well, in this case, Michelangelo, could take a block of marble, and in this case, use a top-down approach to slowly etch away, polish away, and eventually produce the divot. Nature does it in a different way. Nature takes, again, these simple building blocks, things like Lego blocks, and eventually can construct something as beautiful and complex as the Lego did. Well, my lab doesn't use Lego blocks, we use something else. We use colloidal particles. Why do we use colloidal particles? Well, they can be made of, let's say, plastic-like materials or organic materials, biosourced polymers. They can be made with high refractive indices. We can make them in large quantities, and we can make them extremely monodispersed, which is necessary for our photonic color. Where else have you seen colloids today? Well, hopefully in this short presentation right now, you've seen them in this fundamental science by P.C. and Wageningen. We're also interested in crystallization. So can we use, again, these design principles that they investigated to use our colloids to build in photonic color? This is essentially what we did in the lab. And what we get is something that looks like this. So on the top right, is kind of a schematic of what we aimed for, which is called an inverse oval structure. It has air holes inside of some continuous medium. This looks a lot like on the bottom right, which is from the butterfly wing. These are green. This produces this green color. How do we physically make this inverse oval structure in the lab? Well, we start with something that looks a lot like margarine. Margarine is water droplets in oil. Inside those water droplets, we put lots of colored particles. As we densify by evaporating the colloids, the water away, we crystallize the colloids in the top middle, and they form an ordered structure, which is what we need for our photonic color. Then by simply burning away the colloids, we leave the interstitial space, or the space in between, we produce this inverse oval structure. And then hopefully this is schematically clear on the bottom row here. So are these things colorful? Of course, I wouldn't be talking about them if they weren't colorful. The answer is, of course, yes. But not only are they colorful, but we have control. Now that we understand these design principles, we can go back, change the periodicity, change the size, and produce color with different, produce pigments with different colors. So at this point, my group could have said, okay, we're done. We're fundamental scientists, let's leave it at that. That's all we need to do. But we actually wanted to take a step further, and we wanted to produce something that's more applied, something that's called paint. Now, what is a paint? A paint is essentially just two components. It's pigment and a polymeric film former, which we often call a binder. Binders are small deformable particles, here schematically shown on the left. And when the water gets evaporated, these binder particles can coalesce and produce this nice paint film that encapsulates our photonic pigment. Well, we ran into a really key problem with this process that is unique to photonic pigments. We have these small binder particles. These binder particles could easily just go into this porous structure that we have, essentially eliminating all of this color that we've spent so much effort developing. So taking a few tricks, taking again some of these fundamental design principles that we learned from Hans, thank you Hans, we could use knowledge about this electrical double layer to essentially electrostatically prevent the binder particles from entering the pore, and we were able to make photonic paint here on the right that you can apply with a simple paintbrush onto any substrate. Now, the postdoc who was doing this work, she was pretty brave. She was also quite a profound lover of art. She decided she wanted to take 3 of her most favorite paintings and try and reproduce them in our photonic paint. Now, artistry aside, I think she did relatively well, much better than I could do. There's some very clear differences between the two, the real paintings and her photonic paints. One of them is specifically color spectra. So you can very clear that our palette is still relatively limited. We can't produce things that are orange or red. These are still deep fundamental questions that we're working on. How to push the spectrum into the deep red to fulfill the gap between being able to mimic these portraits. We're also moving in a more applied direction. So specifically, there's many steps between this more fundamental proof of concept research that we've done onto the applied side. Specifically in the area of automotive coatings, fashion, and cosmetics. Why are we interested in this? Well, each one of these areas really needs a sustainable long-term solution to coloration. There's also a harsh reality here, in the sense that fundamental science, when I'm looking to apply for funding, almost always needs utilization. These are areas where utilization is crucial and they need fundamental insights. So what we did was we've been partnering with 2 companies, Sherwin-Williams and Interpulse, to really bring this, again, fundamental science more into the applied side. I personally have no problem with collaborating with industry on fundamental research questions, as long as those companies understand that it is in their best long-term financial interests to work on fundamental problems. So to kind of end today, I'd like to say a few more general words about fundamental research. There's this really great analogy that exists with a home. We usually consider fundamental research as foundational research. Well, a foundation without a house is kind of useless, but also you would never build a house without a foundation. So only when both of these come together that you get a nice functioning scientific environment. The specific problem with this analogy, or the difficulty with this analogy, is that it's sometimes very difficult to see the foundation, but it is essential to, again, the scientific community. This is, again, one of the key benefits, I would say, of Wageningen. We have both sides, the fundamental and the applied. There's always going to be a difference between fundamental and applied research. I personally believe that fundamental and applied research should both have a goal. And while any of the PhDs will tell you nothing in research is certain, I think that fundamental research may at one point have a societal impact, whereas applied research most likely will have a societal impact. This is the distinction I would make. This does not mean that as fundamental researchers, we absolutely cannot be afraid to explore and discover these new fundamental design rules. But we also need to be aware of our scientific and natural environment as we look toward the future. So thank you very much for your attention. Happy to take your questions.
Thank you, Thomas. Very nice. Certainly there are questions, hopefully.
Such a nice presentation. I'm just a bit curious as to why you can't make red and orange pigments.
A good science question from a PhD in science. What a great fundamental question. The answer is a second photonic band gap problem. So essentially, as you go further into the red, into 600, 700 nanometers, you start getting a second period reflection that arises in the UV and the blue. So as you push the structure further and further into the red spectra, you essentially revert back into a blue color. So it's very hard to isolate to eliminate this blue color and maintain the red. There has been, again, some fundamental work in this area, but it's still very limited.
Thank you. Just to follow up on that question, does nature provide photonic reds and oranges?
Good question. The answer is actually no. There are no known photonic red colors. That could be for two potential reasons. One, nature actually never solved this problem that I'm discussing with this second period. The other option, which is the more practical option, which I take, is that red pigments tend to be extremely stable. Because the energies are so much lower in the red spectrum, they tend to not actually degrade the pigment over time. So organic pigments in the red are a very long-term practical solution.
Related to that, I think you use quite often materials that already exist in nature, and you copy that in your design. Is that often the case? And do we prove then what is existing in nature?
Well, we use similar design principles. The materials we use, we don't use keratin. We use things like cellulose, actually, in my own research. So we're using, let's say, different materials but the same principles as nature.
I was wondering, it's possible to create edible pigments from the photonic principles?
If it's starting to create what?
It's possible to create edible pigments.
Edible?
Edible.
Edible, absolutely. Yes, absolutely. And this, so people have been working on using starch, so soluble starch polymers, to make edible pigments. So this is an area that is under active research. It's a very interesting question, yeah.
Thank you.
Thank you for a great presentation. I always have difficulty in this divide between fundamental and applied science. And I always think back of a saying from Louis Pasteur 150 years ago, who said there is no applied science, there is only application of science. So I'm wondering how you feel about that.
patterns, these rules that exist in science, and then applying them. Some people, let's say more on the applied science side, have to take compromises in terms of where you begin the process, because there's just so many steps in order to getting into the point of application. So that's what I would say is the role of fundamental science is to provide the first few steps, and then applied science provide it really to the point of application. That would be the divide I make. But I completely agree with this quotation in the sense that we're all just looking for patterns in science that we need to apply.
Thank you for a nice presentation. My question is it possible to balance the amount of money that goes to fundamental research and to applied research? And is it possible to maintain that balance over time?
Is it possible to ever fully balance? This is a very difficult question to ask. It's a very good question. I would say the balance does need to shift from time to time. Right now we're clearly at a time in science where I would say more applied research funding is available. That pendulum swings both ways. The framework I would use is that as fundamental researchers, which I consider myself, we need to always give a perspective that we are doing applied science, but in reality we do fundamental research. There is an ability to not mask, but to be honest and say, look, I'm going to work on this applied problem, but I'm going to do it from a fundamental side. It's up to the general society to then recognize, is that worth pursuing or not? More top-down approach of actually setting a hard limit between this is the budget I give for this is budgeted for that. That's, I would say, way above my pay grade to make that decision, but it's also not really a decision I would ever encourage to make. This boundary should be fluid, depending on who makes the best justification for their research.
Okay, I think that's it. Thomas, thank you very much.